I finished midterm one yesterday, so I can tell you a couple of things. There are going to be 10 questions, and so this is what I designed. Well, you're going to see the instructions, but I can tell you now. So questions 1 to 6, you have to answer all of it. Then you're going to be shown that they are all short answer questions. From questions 7 to 10, it's going to say select 2. You only pick 2, and you answer 2 out of those 4. Now, sometimes, and I know this can happen, so sometimes people tell you, well, can I answer more? You can, but then these are all open-end questions, so it takes me like a whole week to grade everybody's questions. So if you answer more, let's say you decide to answer 7, 8, 9, and 10, I will grade the first 2 that are. Sorry, it's just a lot to grade when I do the open-end questions. So you have 4. Make sure you pick the 2 that you know, and they are from like all topics. So read them, make sure you pick the 2 that you're most certain about, okay? And I will give you 70 minutes. I'm not saying you will need the 70 minutes, but sometimes, because they are short answer, I know sometimes I've had like one student that just takes longer. So that's kind of what I wanted to talk about. So can everybody stay 10 more minutes after class is over?
Mm-hmm.
Is that something that will work for everybody? Yeah, so just to be fair, so we're going to have until, 11:15 or something like that, or 11:20 to finish the exam. So we all start at 10:10, and then we're going to have 70 minutes to complete the exam. If you're done, you're done. It's going to be on Canvas, so make sure you bring your laptop, whatever it is that you're going to use to take your exam. And there's some drawing, so whenever there's drawing, we'll do what I've been doing in the worksheet. You will have something to draw. Anybody has any questions about exam? Okay. So we finished with the driving forces of water flow. And I have your graded actions here. I'll come back to you. So we talked about how water movement through the soil is due to a pressure gradient, pressure potential gradient through the roots, water potential through the xylem, pressure potential, and then evaporation due to difference in water vapor concentration. So this is what we're going to be doing. I have the usual questions that I normally have, right? That opening questions, but this is what we're going to be doing. I'm going to show you the question, and then you are going to be allowed to talk. Okay? And then you will raise your hand and you will answer the question. And if the question is completely correct, of course I'm not going to say 100%, then the entire group will get 2 bonus points, and you will start adding that to midterm points. Okay, so here are some rules, of course. So what I will do is, once the group gets 2 points, prioritize other groups, but if nobody else raises their hand, the same group will be able to answer, but not the same person. Okay. What does that mean? If this group answer and Sam got a point, they can answer again, but Sam cannot answer anymore. It has to be someone else from that group. So now that I'm thinking, so let me see how we make this balance. So I hate to switch groups, but I think having 3 minds over 2 minds is going to be unfair. So, Nick, do you think you can work with Madison for today? Would that be okay? I hate serving groups, but I think that. So you are no longer a group. So you. Okay, so more than Pico, yes, you have to raise your hand, but once you raise your hand and the person that talks, that's going to be your answer, right? So again, I'll try to, if someone answers, I'll try to prioritize other groups. And just to tell you, whenever we hit midterm three, after we take midterm two and midterm three, it's all going to be about specific participation, and it's going to be individual. If between midterm two and midterm three, each person answers a certain number of questions correctly, you can be exempt from midterm three. But that's going to be individual, so this is kind of practice. So I think it's like 12 questions in the entire 6 or 7 lectures. If someone hits that, then you don't have to do it. Last year, half of the class. Okay, so let's see. Okay, you don't want to talk to your group? Okay, so one thing, just before you answer. So these are questions, not all of them will have, only the pink ones will have points. So one of the things is if you think the answer is, I'm going to say like, how hot it is. I'm not going to give you 2 points for midterm 1 for such a simple answer, right? It's going to be, you have to elaborate some more and things like that. So, yes.
Do you want both?
So if you have both.
I think this is the bachelor.
Yes.
There's a major factor, so basically, if air is still around the edge of the leaf, then the outer layer will be very thick. And it's going to make it much harder for water vapor to leave the leaf.
So,
and there are many adaptations that plants have to.
Yeah, not the adaptations yet. That's the next one. Yes. So, yeah, it's mostly the resistance, right? So we talked a lot about how the sun is basically the driving force of transpiration and all of that. So it's basically the diffusion and resistance. Things that the plant really cannot control. Well, some of them they can control, but it is the stomatal resistance and the boundary layer resistance. Okay. So basically, how does that work? So stomatal resistance is, pretty obvious. The more the plant opens stomach, the more water is going to be lost. So if it's closed, it's closed. Right? That's just what it means. We're going to see how this specifically is regulated. We're going to see that today. So that's important. But the other factor is basically the resistance of the boundary layer, which is air. So basically, the wind velocity affects how much water is lost from the wind. So you think about it. Let's say you're a leaf, or you open a door, and basically how much flows in and out of that door also depends on the wind that is basically outside of that. So, which characteristic or which scenario is going to make a leaf lose more water? One leaf that is surrounded by still air, or a leaf that is surrounded by moving air?
Moving air.
Yeah, so moving air, right? So basically what you can see is that here you have the still air. So if a leaf is surrounded by, there isn't a lot of wind, the water that is lost is basically directly related to how much stomach are open. Because there's no other effect than how much is open. There's nothing much happening out there. But when you have a lot of moving air, I change the colors. When you have moving air, then yes, it's the stomach, but also the moving air is going to increase how much water vapor is lost from the leaf, because there's more moving air. So basically the wind velocity will also directly affect how much water vapor is lost from the leaf. So not just stomach, but the air around it.
It's the motto on the roof. So it's so that the sun so not a very big budget.
Okay, would that be short term or long term?
Relative,
Why long term?
because they're always there.
Yes, because a plant cell cannot figure out, oh, it's hot today, let's just have stomach here. Or it's hot tomorrow, it's cold tomorrow, let's just move the stomach somewhere else. Okay, can you think of a short term? Yeah, it's, sorry, both of them are high. So you have to give me one and one.
I don't know, like, can photosynthesis where they do it at night, would that be the short term?
No, that's not short term, because when you think about it, a plant evolved photosynthesis for millions of years ago. So that can be
With the guard cells, opening doesn't be short term. Do they always do that?
Yeah, all plants do that. So I'll give you half of them for now. So I'll give you one. Yes.
Is it switching back and forth between glucose and starch to change the concentration?
No, so this is more, so one of the things is that is something that a plant can, so these adaptations are like some plants do different things. So, like a metabolic pathway is something that that is not really a short-term adaptation in that sense. Can you think of specific things that some plants do, but other plants, so let's say a plant that is exposed to more heat or is exposed to something or a lot of wind, how can they adapt short-term or long-term to regulate leaf transpiration or to minimize or maximize focus? You're gonna have to talk to your partner. Because you cannot say,
Really filtering.
yes.
The leaves, the plants can like adjust how the sun's hitting their leaves. They can like roll them up or
Yeah.
make it parallel to where the
Some
sun's
places
hitting
do
it.
that.
Yeah, so you can roll the leaves, you can switch the angle of the leaf, that's short term. Can you think of a long term? If you give me a long term, you have 1 point for the short term. Can you think of any long term? Good. Now we have bonus one. So, yes, so we have different adaptations in here. We have long-term adaptations, which are trichomes. Okay. This is for like a windbreaker. If there's a lot of wind, plants will develop these little fuzzy hairs, they are called trichomes. And that kind of breaks the wind because the stomata are going to be protected by those little hairs. So the velocity of the wind is not going to affect them too much. Clearly, a plant can increase the amount of trichomes, but a plant that it doesn't produce trichomes cannot suddenly decide, oh, I'm just going to grow away. Another thing is sunken stomate. So the stomate, as you can see here, the somatic complex is kind of sunken, so also kind of very protected. So stomate open and close, and then again the wind is just not affecting it so much because it's protected. The short-term adaptations. So basically, so the opening and the closing of the stomate, as we talked about, is something that plants can do. All of them do. But as we talked about, basically the wind is going to affect how much water vapor is lost. So the rolling of the leaves, so some grasses can roll leaves, and again, decrease how much water is lost. And the leaf angle to the sun. So sometimes through the day, you can see some leaves that are looking kind of like this, and then midday, they will just completely switch the angle so that they get more or less heat. And when you think about these leaves compared to these ones, you can see these here. For example, a leaf that is completely horizontal, here I quantified, how much light you can get. And if you have a different angle, instead of 8, you're only getting 6. So you're decreasing the amount of radiation and heat that you're getting just by switching the angle relative to the sun. That's something that a plant can do through the day, easily just switching. So so let's say this one is So it's important for the exam. So, I didn't have points for this one, but let's say that's gonna be for points. But you have to answer all these. Yes.
So if they're like open like widely, then like they're going to be releasing more water, also taking in like more CO2, which is necessary for photosynthesis.
Yeah.
And then if soil water is scarce, that wouldn't really affect like the opening of the stomata because they'd still be like being hit by the sun. Unless the plant's like out of water, basically there wouldn't be any water for transpiration.
So I think this, just to clarify that, how do stomata behave when the salt water is scarce? You can call.
So I'm gonna jump to number 3.
Okay.
Behaving equally throughout the day. Like there will be depending on like the type of photosynthesis.
Like a regular plant,
Yeah.
normal plant. How do you think they will behave through the day?
I think they'd be open more like during like the heat of the day because there's more like heat energy that they're taking in, so there's like more like, water transpiring from the leaves. Like they have to like be open in order like to let the water escape.
And so what happens at night?
They'd be closed.
Okay. Are they gonna be equally open all through the day?
No.
Sure. So they're not going to be equally throughout the day because if they were equal throughout the day, that's too much water loss. So they're going to have to pick and choose what times are going to be best. I think
Okay.
for most, it's like the early morning is better for them because it's not extremely hot, and there's also enough water in the air that they're not going to lose a lot of the sun because of like vapor and all that. And then as far as like the soil water question, if there's a lack of water in the soil, they're going to have to really pick and choose how often they're conducting their opening because if they're not pulling in any water, they're going to be losing a lot for transpiration. If they already don't have any water down there, they're going to pull whatever's left from the soil and then they're going to dry out. So they have to pick and choose.
Yeah, so yes, that's correct. So, okay, so let's just recap all of these. So stomach, when they are fully open, yes, let's stop talking for a little bit for the week. So, fully open, there's CO2 coming in, but there's a lot of water vapor coming out versus when they're closed. So plants, while they cannot walk away and look for a place with more water, they can figure out what they do based on certain conditions. So they can also regulate stomach when, depending on the availability of water in the soil. So basically, if there's plenty of water, the plant doesn't have to worry. It's like, well, I can open my stomach, even if I lose a lot of water, it's fine because I have a lot of water. So let's allow CO2 in, water out, I have nothing to worry. But just was saying, basically, if there's very little water, then the plant is like, okay, I have little water. What am I going to do? I need to open stomach to eat CO2. But I already have very little water, so if I open the stomach, then I'm going to risk losing even more water. So while the plant will probably have to open stomach, it will have to make sure it doesn't open it too much. Okay. At some point, if it's completely dehydrated, it will just close it. And then the plant will die because of water not coming in, but it's also because it's not eating, because the CO2 is what's giving it carbon. And then stomata, stomach, a single one, doesn't really behave equally through the day, even when there's plenty of water. Also, stomach tend to be more open early in the morning. When the sun starts shining, we know the sun is required for photosynthesis. We're going to talk a lot about that later on, but actually stomach, with no sun, really you're not going to have stomach open. There's one of the cues there. So the sun starts coming out and it's not too hot, so it's the perfect time. There's water available, it's not too hot. Let's open the stomach. Maybe if it gets too hot in the middle of the day, let's close the stomach a little bit, either fully or just a little bit. And then maybe later during the day, you can open them again if you need to open them more. Because again, there's still sun, but you're not risking losing too much water based on transpiration. So they do not behave equally through the day, even when there's plenty of water, the stomach are always regulating how much they're open and how much they're closed. And so, yeah, so that's basically stomatal resistance. How much open or closed they are, and that tells the plant how much water it uses.
I'm blanking on anything else.
Yes. Okay. You have to answer both. Okay. Okay.
Alright, this is the guard cells, this is not maybe the subsidiary cells.
Okay. Yeah. So the somatal pore,
Yeah.
the guard cells, and the subsidiary cells. Okay.
And then grasses have more of a dumbbell shape, and more like a bar, and have
More than what?
an elliptical shape.
Yeah. So they are called, yeah, in the elliptical shape are called kidney shape. I don't know why, but they are called kidney shape. Yeah. So there are three main cellular components. So we have basically the pore that is just a hole, but it's still part of the somatal complex. And then you have two main components, the guard cells that are just surrounding the somatal pore, as you can see here. And then the guard cells are surrounded by another type of cell known as the subsidiary cell. Another thing that is important is that grasses tend to have these dumbbell-shaped guard cells. I'm going to show them larger in a minute so you clearly see the difference. And then this kind of elliptical shape, they are called kidney shaped, is in almost everything that is not grasses. So from dicots to some gymnosperms, some ferns have similar things to stomach, and all other angiosperms will have this. Also, all grasses, as far as we know, have both guard cells and subsidiary cells. Some of these kidney-shaped stomata sometimes lack subsidiary cells. But the job of subsidiary cells, that is super important, and we're going to talk about it in a minute, is basically in the case that the subsidiary cells are not present, there is some epidermal cell that just does the job of the subsidiary cell. So you need guard cells and subsidiary cells for stomach to open and close. So when you think about the dumbbell-shaped, this structure, right, so you can see basically this would be the guard cells. You cannot really see in this case, but this would be kind of like a cell wall in here, and this, the pore is very close at this moment, and this would be the subsidiary cells. And if you were looking at it from, not from the top, but from the side, you can see basically that the pore is just a hole that is connecting the interior of the leaf with the outside. But just how much these cells allow this pore to open and close to regulate how much CO2 comes in and how much water leaves. So, oh, okay. So, oh no, but your group already has points. So let me see.
Okay, so when the guard cells like fill up and stuff like that, when they open, they kind of push in the opposite direction, and like vice versa. When like the subsidiary cells like fill up, they kind of like push the guard cells together, cleansing it.
So yes, but so one thing is like if you have the guard cells, right? Let's say this is the pore, right? Oh. This is the pore, and you have cells. No, wrong cells. Surrounding them. Why is it that when they gain water, the pore opens instead of the opposite? Why when you gain volume, instead of this being smaller, it's actually bigger?
Because it kind of like fills up in the opposite direction.
Yes, what do you mean in the opposite direction?
So it pushes more on the subsidiary cells than it does on like over the pore. Like the turgor pressure, like when it increases and stuff like that, it like forces to go in a different direction. I don't know how else to explain it.
Can you blow it?
Can I draw it?
If you want, I just want to
I
make
guess
sure
I
I
could try. I mean, it's worth it.
I mean,
It's worth
you
a
can
shot.
try it. Yeah, I mean, why not?
So this
What
is
do you
the pore,
mean
right?
different directions? Yeah, I mean, or you can
So
go
they're
better
gonna wanna
cell.
go that way, and they fill up.
So how would they look? Can you draw how they will look like?
They're more like
Yes,
yes.
yes. How would you draw?
I guess it would be just more like this, like they kind of go like that.
Okay.
Kind of a way you're looking for.
Yeah, I mean, yeah, so it's not exactly like that, but hey, that's close enough, you know? So in the sense, it is correct because they actually become more like this, right? So they have different, the fibrils inside them are located in a way in which they really swell up more in some areas than in other areas. And yeah, that's correct. Actually, that's good practice if you ever take your qualifying exams for a PhD, you're gonna be in the board for 4 hours. So, so you do that once. Good practice. Okay. So it's all because of the deposition of the cellulose microfibrils. So as you can see, we briefly talked about how the microfibrils, are located. But so it's more basically, you see, like they are more reinforced in this particular. So if the microfibrils are more reinforced, like in this way, it's going, when it swells up, these parts are going to be more like strongly constrained, and it's going to swell up more from these sides because it's most constrained on this part. Okay. Also, when you have these cells like this and you have microfibrils in this way, then when it expands, in this way, yes, you're going to expand more like this. And so, I think I did a drawing here. So the dumbbells is like, think of dumbbells, at the gym. If you have like, the 5-pound dumbbells, right, the things, and you try to put them together, they're kind of holding between both grip handles is going to be very small, right? If you have the same size of the grip handles, but a larger weight, and you try to put them together, they're going to be more separate, right? Why? Because you're filling out specifically these parts, that the weight just borders of that. And then in the kidney-shaped cells, I don't have such a good example as to the dumbbells. I think the dumbbells is easier. But it's just like basically think of like I don't know, inflatable ends, and then this part swells out. And then as this swells out and this part grows more, it separates and opens the pore. So both of them are gaining water, and the pore is just getting dark. This one basically means how do both of them in complex? What's happening to one, what's happening to the other one? How do they regulate the amount of opening? Give me 15 more seconds, please.
Makes sense. It's what you're saying. It makes sense. That would be what they would do to regulate.
Some minute detail.
Yes, specifically.
Yes, but how? You have to talk about both of them. What's happening to one versus the other?
If the guard cells are swelling, they'll trigger pressure. The subsidiary cells would be great tension, which would cause it to heal. And just opposite.
So, yeah, okay, yeah, so one does one thing and one does the opposite thing, but how do they, basically, so how were they, explain it, but how are they both in conjunction? Because you need both. How is it that both of them, what is the interaction that's happening that is allowing one of them to regulate the other and those ones sweating or not sweating and opening the other? Yes, but yes, so you can say pressure, but basically, if you tell me what's happening, exactly what one of them is doing and how it's increasing pressure on the other, I can. And also remember, living cells never develop tensions. So you can have less positive pressure, but never negative. Tension is only developed where? What we talked about. In the silent, yes.
Okay, so is it just the both pressure and pressure? I'm not sure.
Okay, so both have turbo pressure, but how? Basically, how do your subsidiary cells, what happens between both of them? What allows one of them to regulate the other? Basically, that's what happens. One of them does something that regulates the other. Okay.
It's the subsidiary cells control the solute concentrations, so they exchange solute concentrations, so the guard cells can take the water to swell.
Okay, so yeah, so solute concentration, that's the key. Who gives solute to who?
Subsidiary gives it to the guard cells.
So subsidiary cells give solutes to the guard cells. And then what happens then?
That allows for the influx of water for it to expand.
Yes. So the whole point is the solute concentration is changing. And by changing the solute concentration, you lower the water potential. And as you lower the water potential, you make water go into the cell that has a lower water potential. And that swells up the guard cells from donating water from subsidiary cells, and then vice versa. So basically what happens is the subsidiary cells donate solids to the guard cells. So the subsidiary cells would be these ones in green, and then the guard cells would be the ones in black. And so these orange dots, let's say they are solids. So when it's time for the stomatal pore to open these solutes, one of the most important solutes that is donated is potassium. Okay? Potassium is key in this regulation. So potassium and some other ions, but mostly potassium goes in here. And then what happens to the solute concentration based in the cells? Well, the solute potential in the cells, remember, will decrease because solute potential is opposite to solute concentration. So solute potential decreases, the water potential decreases, and as the water potential in the guard cells becomes lower, water flows from the subsidiary cells into the guard cells. And then, the dumbbell shape, the guard cells gain water, expand, become larger, and that opens the stomatal pore. It's all because of dominating solutes and affecting the water potential in the guard cells. This one, I didn't put this here because, I don't know why I didn't put it pink, but I guess it can be pink. Yes. You have at least two.
What's that? Oh,
At least
two, okay.
Oh.
So one of them would be like sunlight, like direct sunlight onto the leaf or the plant.
Yes.
And then the other one would possibly, there's two more that we thought of. One of them could be like evaporation, like that could also play a role in it. And then water vapor, yeah.
Water vapor, what?
Like the amount of water vapor in the air around it.
Yeah, so the water vapor difference between the inside and the outside of the building, right? Yeah, so basically, one of the things is directly light, right? Like activates, these are not the only ones. So temperature and basically the leaf temperature and the temperature of the air basically directly regulates the water vapor concentration. I'm not going to go into details, but basically the warmer it is, the more vapor it can hold, right? That's why sometimes, when it's hot, you kind of feel things are more humid and it's literal. The warmer something is, the more vapor it can hold. So the water potential and, basically the input surface. But the most important things are leaf temperature, water, light, and the difference in water vapor concentration that will regulate the smell of it. Remember, so as you can see here, there are clearly many things happening in the guard cells, but one of the most important things is clearly water is coming in, and then potassium is the main solute that goes into the cells. And then, at night or under water stress, then what's going to happen is that potassium is now going to leave, and as potassium leaves, that lowers the water potential, and then water goes back from the guard cells into the subsidiary cells, deflating them, and everybody goes back to normal and the water.
CO2 as compared to PGOs release.
Yeah.
Right, they just try to use them all together.
Versus how much water is in the air because
So if one was there,
it's in cooling carbon, but water outside is really cold. Then you're gonna lose a lot more water to it's the other way. With a lot of water.
This is the last question, so I want to give 30 more seconds.
Okay. Thank you. Yeah, strategy parts and tripping us up.
I know sometimes because these topics you sort of know, but the answer and if not everybody is willing to speak up really, and it can be just shyness, whatever it is. I was there until I realized I was always telling the answers to the person next to me, and then they were speaking out, and then the professors thought they knew. So I was like, that's not gonna happen anymore. So it took me to my PhD to get to do that. But then I thought, well, I'll probably not take any more classes, so it's now or never. So, one of the things is that, I'm just letting you know, I make mistakes. I screw up all the time in class. Sometimes I get home and it's like, I taught the worst class today ever I did. And so what? I mean, what's the worst thing that's going to happen? I said something wrong. I said something funny. I said something. I'll correct it maybe next class. You don't even remember, and I'm still remembering the mess up I did. So I'm just saying, even if your answers and for the future, they are not right, like, okay, so nobody is going to be affected by any of that. So just letting you know, nothing happens.
Okay. Gosh darn shit, jeez. I didn't think of anything for any of them. So apparently it looks like there's a lot more than one.
Okay, so who's raising your hands? I think I've seen like 3. Okay, so I see 3 hands. Okay, so 4. Let me see this. So you two have like 4 points. So black, no. You have 2, and you also have 2. So it's only 3 for. Okay, that's, oh gosh, so.
You can just talk to it.
Yeah, why not?
Send your representative.
So I think it's, yes, so for me, it's groups 6 and 3. I just numbered the groups. So rock, paper, scissors? Yeah, so, yes, with sound. Oh gosh.
Alright, Sam wins.
That's 2 out of 3.
Maybe it is something easy. Okay, so what is transpiration ratio and what strategies have plans developed to watch it?
So transpiration ratio would be like the amount of like CO2 entering the cell versus the amount of like water leaving. So these are coupled. So yeah, it's like water vapor enters, CO2 has to exit. And then like some of the strategies would be like stomata on the bottom of the cell, not allowing gases to just like escape out the top. And then like opening during like specific times of day, when like they open like preferentially in the morning when like vapor pressure and the humidity are going to be like higher around the leaf, but they're gonna be losing less water and still able to like change some of that CO2.
Yeah, so transpiration ratio is basically the rate of absorption of carbon per water loss. So how much water plant on average loses per carbon that is fixed into shoots. Now, those strategies of closing stomach and all that, they can regulate kind of how much water is lost by a plant in a moment, but a plant cannot really control its transpiration ratio. It cannot really control how much water comes, how much carbon it fixes per water that is lost, because it all depends. So basically why is that important? Because if I don't open my stomach a lot, they have no control over how much CO2 is in the environment. So they can decide, I'm going to open this more or less. But on average, we'll take the same plant species, they will have like an average transpiration rate. That's something that a plant species cannot modulate. So, do you guys want to give it a try? So that gives you 1 point. I'm not saying it's wrong, but that is, you can regulate how much water is lost by transpiration ratio, the term that is basically the efficiency of CO2 fixation is basically fixed between taxa and inputs. Do you think of any strategies that plants use?
I was pretty much going to say the same thing, but there's also that they can keep lower levels of CO2 and water in the actual cells so that there's more of a gradient that takes in.
How do they control the CO2 gradient inside the cells?
By using your photosynthesis and fixing particles.
Yeah, so you're into something. How do you call that? That's exactly the description. How do you call that metabolic pathway that allows plants to concentrate the amount of CO2 inside of the cells?
Respiration of cell.
Yeah, so you have the most difficult part, that is the mechanism. How do you call that? Anybody wants to tell me how to call that?
Is it carbon fixation?
No, I mean, carbon fixation is the whole process. How do you call that type of metabolism? Or that pathway?
One of those pathways that typically like the first photosynthetic product is going to determine that. And so most plants have a free carbon product, whereas a lot of plants that have a lower transformation ratio are going to form a four carbon product that lowers the concentration of CO2 and just allows CO2 to become more efficient.
So how do you call the photosynthesis that instead of a 3-carbon product has a 4-carbon product? Yes,
It's C3 versus C4.
yes, C4 photosynthesis. Yes. So it's called C4 photosynthesis. So it's a whole process of evolution that divides plants into the regular photosynthesis we've been learning about since high school, and the new photosynthesis you're going to learn about because one wasn't enough. You're going to learn about 3 types of photosynthesis: C3 photosynthesis, C4 photosynthesis, and CAM.
Alright.
So transpiration ratio. So the regular photosynthesis that you know is called C3, and it is because the first product, and we're going to extensively talk about photosynthesis. That's the part in midterm 3 when you have the option to answer questions and all of that. The first stable product that you fix is a 3-carbon product. It's called C3 photosynthesis. And so the water use efficiency is 1 in 400. So basically a plant will lose 400 molecules of water per CO2 that is converted into sugars. Very inefficient. So why is that? Because there's on average, not on average, there is low CO2 in air. So with new CO2 is increasing in air, but that's the only part that is good news, just that. The diffusion rate, also CO2 basically moves slower than water. So it takes longer for CO2 to come in than water to leave. And also the assimilation pathway. So when you think about it, the CO2 that is in the air has to enter the cell and then cross the membrane and then enter the chloroplast, where the Calvin cycle happens. While water is just there in the space and it's ready to go. So it's very inefficient. So C3 plants, right, the photosynthesis that you know, and by photosynthesis I mean more carbon reactions because that's the part that is different. So wheat, rice, basically there's many plants that do this very efficient photosynthesis. But other plants, and we tend to think of plants that are in more like tropical areas, warmer areas all year round, like sugarcane, soybeans, and corn. They are called C4 plants, and we're not going to be talking about C4 photosynthesis just yet. Important thing to remember is you can see the efficiency is much higher. By accumulating, so what they do is they bring in the CO2, and instead of producing a 3-carbon product, they do something else and bring a 4-carbon product that just makes it more efficient. We'll talk about that later on. But because it's 4 carbons instead of 3, it's called C4. And so, in C3 plants, you have CO2 coming in, and then coming into basically mesoscale cells and doing the Calvin cycle. In C4 plants develop a whole new type of cells called bundle sheets. And then photosynthesis happens somewhere else. So it compartmentalizes, it kind of increases the amount of CO2 here versus the air brings some CO2 and then that's photosynthesis. So it separates photosynthesis in space. And the last one is CAM. Now you can see it's much, much more efficient. You're only using 50 molecules of water per CO2 that comes in instead of 400. And CAM separates in time. So you fix CO2 at night initially, and you complete the rest of the Calvin cycle during the day. So you open basically stomach at night and not during the day. And these plants are just extremely Not rare, but specific, yes.
I was going to ask, what kind of plants would you use to can?
So many basically desert arid plants, very few plants will do can photosynthesis. It's very rare. Not very rare, but yeah. The type of plants that can are very specific. That will open stormy at night, mostly desert plants.
Thank you.
So what it directly impacts is how much water you lose. And of course, like even if a C3 plant can regulate a little bit stomach opening and closing, you will never get to the levels of a C4 plant or a CAP plant. Yeah.
Can you explain more specifically why they're using less water for a carbon molecule?
Yes. So let me see how much. Yes. So there are many things that are important here. So we'll cover this extensively in the future, but one of the things is rubisco. So you probably know rubisco, right? The most abundant enzyme on Earth. Rubisco is the enzyme that does this. This is rubisco, right? This one here. Rubisco is doing that well, but rubisco is very messy. Sometimes rubisco, instead of producing this and grabbing CO2, sometimes it grabs oxygen. Why? Messes up. So instead of producing this, grabs the carbon and wastes the energy, so brings in the carbon, but instead of doing a carboxylation reaction, does an oxygenation reaction. And while the CO2 has come in, it actually does the wrong reaction and wastes the CO2. And in turn, instead of producing a 3-carbon product, it only produces a 2-carbon product that is actually toxic to the plant. And that is directly dependent on temperature. So while climate change increases the amount of CO2, and rubisco can get more CO2, clearly, the warmer it is, the more messed up rubisco is. So while there's more CO2 and potentially can fix more carbon, it messes up and does oxygenation instead of carboxylation and messes up. So what happens also is, in this case, rubisco doesn't mess up because something else, there's another enzyme that takes the CO2 and grabs it and fixes into something else. And only then, when that C4 product is there, it releases a CO2 inside of the cell that rubisco, here you go. This is just for you. There's no way you can mess up. Please do your job. And so that's what happens, literally. So it's temporarily fixed into something, and then the CO2 is cleaned and released almost in rubisco when it's not competing with oxygen so much in these bundle sheet cells. So it facilitates that. And in this case, it's a similar process, but because it's uptaking CO2, so you can see still C4, so it's a very similar strategy. It's fixing the CO2 into something else, not involving rubisco, but a different enzyme that doesn't mess up that much. And then it does that and stores it as a C4, actually as malate at night, and just stay there. And during the day, because rubisco needs sunlight to work, during the day, it says, hey, rubisco, here it is, do your job, but only during the day. So it's actually even higher because the stomach are fully closed during the day. So it's 3 completely different pathways. And these ones evolve a completely different type of cell to be able to do that. Any questions? Good. Okay, so I will let you know after class today how many points you have for different ones. And then I will see you here on Monday. Remember, scheduled to be here 10 more minutes. You're going to have 70 minutes.